Hello, everyone. Thank you for joining us today. I'm Yasmina Greco. I'm with O'Reilly Media, and I will be your host for today's webcast. We would like to begin today's event by saying a big thank you to SIG, Software Improvement Group, for sponsoring our event today, and let you all know. Software Improvement Group investigates, measures, and evaluates the technical quality of more than 500 corporate software systems each year. At SIG, we experience that not only software is eating the world, but also enterprise IT is pushing the envelope. Organizations are being challenged more than ever to embrace and leverage digital innovations such as the cloud, big data, social, and mobility. However, this is proving to be a tough topic to tackle, given that most of the current IT systems are not prepared for such challenges. Even worse, we see that 85% of IT's budget is spent on simply keeping the existing lights on. To stop this downward spiral, the software industry needs to demonstrate the importance of software quality to everyone that uses software to reach their goals and realize their dreams. Do you know how the source code of the software determines quality? From our side, we have seen our fair share of source code, and now we want to communicate that knowledge to you. Thank you again, SIG, for sponsoring our event today. Folks, joining us today, we have Rob Vanderleek and Željko Obrenović from SIG, and they're going to talk to you about building maintainable software for sustainable business growth, 8 best practices. Rob Vanderleek is Senior Consultant in the Software Improvement Group, and after obtaining an MSc degree in Software Engineering from Delft University of Technology in 2005, Rob joined SIG as a software quality consultant. Working at SIG is for Rob the closest thing to being a software doctor. In his role as a consultant, he combines his thorough technical knowledge on software engineering and software technologies to advise clients how to keep their systems in shape. In addition to being a consultant, Rob fulfills a leading role in SIG's internal development team. This fulfills a leading role in SIG's internal team company. It's Rob's ambition to leave the IT industry a bit better than he found it. Also joining us is Željko Obrenović. He's a principal consultant for the Software Improvement Group, and he's an experienced practitioner, researcher, and teacher. At SIG, he conducts detailed technical analysis of software-intensive systems, translating technical findings into actionable advice for management. Before joining SIG, Željko worked as a consultant at Backbase, an assistant professor at the Technical University in Eindhoven, and a researcher at CWI in Amsterdam. He is a member of IEEE Software Advisory Board and writes regularly about software and interaction design. Folks, we're very excited to have Rob and Željko with us today to present this webcast for you all. As we get the event started, I'd like to go over a little housekeeping to help you get the most out of today's webcast. First, you'll want to open your group chat widget if you haven't already done so. This is where we can interact with each other during the event and where you can submit your questions for Rob and Željko. We find that our audiences usually have a lot of good knowledge to share, so we encourage you all to chat freely during the event. However, if you have questions for Rob and Željko, please preface them with a capital letter Q. That way, we'll know it's for them, and we can make sure we see it for Q&A. You can also open, move, and resize any of the other widgets. We do want to let you all know that we are recording the webcast today, and we will have the recording ready usually within 48 hours. And folks, at this time, it is my pleasure to turn the program over to Rob and Željko. Hello, gentlemen.
Hello. Thank you, Yasmina. My name is Željko Obrenović, and together with Rob, I'm going to present you 8 best practices for building maintainable software that can support your business growth. Now, we decided to start our story with one example from one of our recent projects. So what you see here on the screen is a dependency diagram of one of the systems we recently analyzed. This is a view of a system that has around 30 components with more than 300 connections among these components and around 80 places with cyclic dependencies among these components. Now, without going into details about this system, on first glance, this looks like a mess, and it is by all means a mess. This system is practically impossible to understand, maintain, or test. It is what we call unsustainable system. So you may ask yourself how this happened. And the answer is very simple. It happened one line of code at a time. That means this is not a consequence of one big error that someone made in some moment. Rather, quite intelligent and competent people working under pressure to create functionality have gradually introduced complexity to the point that they were not able anymore to handle. And this is one of the main themes of this webcast, how to prevent this from happening. And the answer will be the same, one line of a code at a time, by following a few basic guidelines that we are going to introduce here. Now, before going into details about our guidelines, let's make a step back and briefly explain who are we and what are we doing. So Rob and I are working as consultants for Software Improvement Group, and we are a specialized consultancy firm for analyzing costs, quality, and risks of software systems. We have strong academic connections. We started a spin-off from Dutch Center for Mathematics and Computer Science in Amsterdam. And what we are doing is providing advice based on automated source code analysis. So we are building tools for automated source code analysis, but we also try to bridge this gap between technical details and business impact, trying to explain what are the consequences of particular technical elements on business value. We've been doing this for the last 15 years. We've seen more than 1,500 systems and measured 100 different technologies. Now, this previous slide, or this slide about our background, is also important for our story, because what we are doing is not only measuring low-level technical details, but also providing a link between these technical details and business growth. And this technical picture that I showed you in the beginning, showing unsustainable system in technical terms, also has its equivalent on a business side, because it also leads to unsustainable business growth. So this system, while starting as an initial success and while being a driver for business growth, in the end cost more and more to maintain and to keep going, and in the end worked against the business growth, costing more than actually it produced. And that's basically what we are going to talk about, how to prevent starting this unsustainable business growth, how to prevent your software working against you. Now, how this starts, how this happens, there are many patterns. We observed many patterns in practice about this. One of the common patterns is what we call the cycle of unsustainable software development. So what often happens when your software starts to be a success, you need to grow, and normally you need new developers in your team. If your software is not easy to understand, if it's not easy to maintain, new developers may have difficulties to find their way into this code, and they may actually fear to touch existing code. This fear, combined with the pressure to quickly produce or add some new functionality, may lead to situations that changes in codes may not be optimal, but developers may introduce different workarounds, for example, copying pieces of code on different places. When you start to introduce these workarounds, your system complexity starts to grow, and you end up in a system that grows quite rapidly, both in size and complexity. And when you have a big system that is also complex, your existing team may not be able to maintain it, so you need more developers. And then you start the cycle again. And once you start the cycle, you quickly end up in a situation that we show you in the beginning. So how to prevent this cycle from starting? So one of the key terms that we are going to talk about is maintainable software. And we have three basic principles that we want to present and elaborate in this presentation. So the first is that sustainable business needs maintainable software. If you want to have software that supports your business and follows your business and drives it. You need a software that's easy to maintain. The second principle is that maintainable software is not some magic construction, but follows the basic principles that you need to build things that are small, simple, and flexible. And the third principle, or axiom, is that maintainability is measurable. So it's not some vague term that you intuitively understand. It's something that you can accurately measure and that way keep under your control. And that's basically our way, how we look at maintainability. So by following these first two guidelines, we use our tools to measure maintainability and came up with recommendations how to work. And in past 15 years, we've been measuring maintainability quite a lot. We've seen more than 1,500 systems, and not only one version of these systems, but in total more than 40,000 versions of these systems in 100 different languages. And total, we analyzed more than 7 billion lines of code, and we are actively monitoring a few hundred of these systems, effectively analyzing around 27 million lines of code each week. And based on this analysis, we were able to extract quite a lot of useful knowledge and information. In general, when we talk about maintainability, there are three things that you can measure and you need to measure in order to reach this goal of having small, simple, and flexible software. The first is, of course, size, because smaller is always better for maintainability. The second is complexity, for example, control flow complexity. And the third is coupling, the level of interdependence. Of course, there are many tools that can provide these measurements. But what you learn is that measurements alone are not enough. So what you also need is some practical guidelines that you can apply in your daily practice about how to avoid coming in particular dangerous situations. And from these measurements, we basically identify the number of guidelines that you need to follow. But behind all these guidelines is the following story. And that is that for many of these measurements regarding the size, complexity, and coupling, you have situations that if these values are behind some threshold, you can go quite a long way. For example, if your system stays small, you can easily maintain it for a long time. Once when the values of your complexity, size, or coupling are above some threshold, then things can go quickly in the wrong direction, get more complex. And once when your system reaches behind level of complexity, like the example that we showed at the beginning, then there's no way back. It's very difficult to do anything to make things easier. And from these measurements, this is pattern that we see for most of the measurements that we do for maintainability. We extract the guidelines, which are in essence road signs telling to you, look, now you're approaching a tipping point where complexity of your system, size of your system, or the coupling of your system may be beyond your control, and now it's time to do something about it and go back. So this is how we came to our guidelines from these measurements. And Rob will, in the next slide, start to present you each of these guidelines in more details. Before that, just to illustrate three basic principles that we follow behind these guidelines. The first is that maintainability benefits most from adhering to simple guidelines all the time by everyone. Means there's no magic solutions, there are no silver bullets that can solve the problem in your maintainability. You need to do it one line of a code at a time, and every individual contribution counts. The second is that maintainability is not an afterthought. You should address maintainability from the very beginning of your development project. And the second is, of course, that perfection is impossible. You cannot follow all the guidelines perfectly all the time, but you have to be aware that the more of the system complies to these guidelines, the better. So now we finish this introduction, and I think you're now aware why we think that maintainability is important for supporting sustainable business, and we explain how we came up with these guidelines, and Rob will now explain you concrete guidelines with some concrete examples.
Okay, Shelko, thank you for the first part of the webcast. In the second part, we will show you the 8 guidelines that we think are very important for building maintainable software. In the slide that you see on the screen, we have listed all the 8 guidelines. And as you will notice, the guidelines are pretty simple and pretty short. This is important because, as Željko already explained, these guidelines need to be applied every time new code is being written or code is being maintained in your software system. You will also notice that the guidelines contain specific threshold values. These values are what Željko introduced as the tipping points, after which code becomes less maintainable. The guidelines are there to prevent you from going over a tipping point. The third thing to note about the guidelines is that they work on different levels. As you can see, we have 4 different levels, from unit to system, and we have a guideline or more guidelines for each level. In the following slides, I will go over all of the guidelines and show you examples of how the guidelines work in practice. And I will use Java as a programming language to show you how the guidelines work and what they actually mean. But these guidelines are technology independent, and that means you can apply them to any modern programming language. In fact, it is very typical that modern software developers use multiple programming languages in their daily work. For example, to work on front-end code, we typically see JavaScript or TypeScript, while the back-end code consists of Java or C#, or maybe you're using another programming language. Still, all the guidelines that we showed to you today apply to these different technologies. The guidelines contain generic terms for the different levels to which they apply. And to show you how you can map those different levels to different programming languages, I've created a slide with a couple of examples of the different levels to which the guidelines apply. The first and lowest level of the guidelines is the unit level. And when we talk about units, we mean the smallest executable blocks of code in your system. For example, if you're working on Java or any other object-oriented programming language code, a unit is a method. But maybe you're using a different programming language that has functions or procedures. So when we talk about units, that is the level of code that we're talking about. Above the unit level, programming languages typically support a grouping of units. For object-oriented languages, typically you group your methods into classes. When we talk about the module level, this is the level that we mean. Above the module level, we have the component level. And the component level is basically the high-level decomposition of your software system into separate architecture areas. A component can be multiple things, but typically we see that the component is a top-level directory that groups a related set of code files, or you can also use language-specific concepts to define your components, for example, packages in Java or namespaces in .NET technology. On the highest level, we have the system level, and the system level is what we mean with the complete code base of your system. So that's all the code that's being maintained in all the different technologies that you use, and it's the code that's being maintained by a single team of developers. So now that we got the definitions clear, let's move on and look what the guidelines actually mean in practice. And we start, of course, with the lowest level guidelines, and those are the guidelines that work on the unit level. We have 4 guidelines for the unit level, and I quickly go over them and show you some examples after this slide. The first guideline for the unit level is to limit the size of your units. And we put a limit of 15 lines of code per unit to keep your units easy to understand, easy to test, and also easy to maintain. The second guideline for the unit level is about complexity of units. And we put a limit on the number of branch points in a unit, and that number is 4. A branch point is a statement in application in your code that introduces a new control flow path. For example, if you're using a technology like Java, a branch point can be a loop statement such as for and while, or a decision statement such as if and switch. The third guideline is about the number of parameters. We advise you to limit the number of parameters per code unit to 4. If you do this, it becomes much easier for developers to understand, looking at the interface of your unit, what the unit does and what it requires as input. This has a positive effect on the code reuse in the system and also on the maintainability of your code. And the final guideline for the unit level is about duplication. Blocks of code that are duplicated, which are 7 lines or longer, should be prevented in the system. Code duplication leads to a lot of maintenance. First of all, it grows the total size of your system. But secondly, we see that in maintenance, when code is duplicated, it frequently happens that bugs, for example, which are found in one part of the system, occur after a while at another part of the system. And this is something we want to prevent if we want to have a sustainable software system. So these are the definitions of the guidelines. Now let's see what they actually mean in practice. For that, I start with 2 Java methods that are compliant to the unit level guidelines. On the screen, you see 2 methods that we extracted from the open source code base of Jenkins. You might know Jenkins. Jenkins is a continuous integration server. We use it also at SIG for our continuous integration pipelines. And Jenkins is a Java code base. And we extracted from that code base 2 example methods that comply with our guidelines. On the left, you see a method which has 13 lines of code. The method has 3 branch points. Those are the 2 for statements and the if statement. And the method takes 1 parameter. Also notice that this method has, the name of the method is do autocomplete, and it has a clear responsibility. This method is part of the auto-completion functionality in Jenkins, and for now it's not important that we understand exactly what the method does, but as you can see, it is easy to get an understanding of the method if you read through the code. On the right side of the slide, we see another method, also from the Jenkins code base, which also complies with our guidelines. This method is a bit longer. It has 15 lines of code, but that's still okay for the unit level guideline. It has 4 branch points, so it has an extra if statement, which is also still in line with our guideline for number of branch points, and it has 1 parameter. Also notice that this method clearly has 1 responsibility. The name of the method is called isMultipart form, and this method clearly checks if the given input string is a multipart data form. So these are 2 examples of what we consider code that is compliant to the guidelines and what we also consider maintainable code. Unfortunately, in reality, we see that not all code is like this. As an example of a piece of code that we typically see during our analysis work, we've put the following method on the screen. This is again a Java method, but now this method no longer complies to our guidelines for maintainable software. Actually, it violates 2 of the guidelines. The first guideline it violates is that the method is longer than our guideline says. So we have a guideline for unit size that has a threshold or a tipping point of 15 lines of code. And this method actually has 38 lines of code. Also, this method is not compliant with our guideline for the number of branch points. Our guideline limits the number of branch points to 4, while this method has 5 branch points. The result of writing code that is not compliant to the guidelines, and as Shelko explained, is actually past the tipping point, is that things start to happen in the code that are not optimal for maintenance. For example, as you remember, the previous 2 methods that we've shown that are compliant, they had a single responsibility, and it was clear from their method name what the actual functionality of the method is. This method has multiple responsibilities. Again, it's not important that we completely understand now what the method does, but if you quickly scan over the code, you can see that this method does a lot of things. First of all, it opens a connection to a database. After that, it performs a query on the database, a select statement, for which it gets a result set. Then it will build a JSON formatted output string, and it will append all the valid items of the result set to this JSON formatted output string. That is a lot of responsibilities for a single method. And I'm sure that a lot of you will find it very easy to split up this method and to extract the different responsibilities to different methods. This is how our guidelines work. They indicate parts of your code that might become a maintenance problem in the future. And maybe you think that this method is still a maintainable method, but that is just because this method is not so far over the tipping point. It only has 38 lines of code and 5 branch points. What we do experience in practice, that if code is beyond the tipping point, it typically only gets worse in the maintenance phase. For example, in the photo you see on the screen, actually there is the 2 presenters of this webcast in this photo. On the front you see Shelko, and in the back it's me. And we're holding the printed version of a single Java method. So this is a bunch of sheets of papers glued together that contain one method. And this is clearly code that is way beyond the tipping point that our guidelines try to prevent you from reaching. So, one more example of a violation of our unit guidelines, and this is the guideline for code duplication. For unit level, we have one guideline related to duplication, and that says that all blocks of code that is found multiple times in the system, all blocks of 7 lines or more, should be removed on the screen, or should actually be prevented in new code. On the screen, you see 2 methods, and these 2 methods are, again, Java methods. And what happened here is that the developer applied a workaround. We don't know why, but what happened here was that the method on the left, it already existed in the code base, and when in maintenance mode, the developer added a new method with similar functionality, there was a quick copy and paste action, and that has actually led to a violation of the guidelines, of the duplication guideline. Still, the methods themselves, they are not that complicated, not that long. As you can see, they still comply with 3 of the 4 unit level guidelines. The methods are 15 lines. One method has 2 branch points. They both have 1 branch point. One method has 2 parameters, the other 1. But still, this is a violation. It's a small violation, but still a violation. And actually, the good thing about small violations is that it's typically also easy to fix them. For example, if we apply a refactoring method, a refactoring technique, the extract method refactoring, then this code duplication is quite easy to prevent. And if the violation is still small, this is a small effort to keep your code maintainable. Again, this is why we created a list of 8 simple guidelines that you can apply in your daily practice of software development. So, those were the 4 unit level guidelines, and now we move one level up to the module and component level guidelines. Remember, a component groups units, so if you're working with an object-oriented technology, your components or your modules are typically classes, and components in their turn group related code modules. For the module and component level, we have 3 guidelines. The first guideline is to limit the size of code modules to 400 lines of code. In the next slide, I will explain why we chose that threshold and what it actually means in practice. For the component level, we have 2 guidelines. The first is to limit the amount of components in your code. So remember, the components are the high-level decomposition of your system. And we advise you to create 6 to 12 components of roughly equal size. The third guideline is to prevent any cyclic dependencies between components. If you follow these guidelines, it will benefit maintainability of your system, because by following these guidelines, your modules or your classes will have a clear separation of concerns. Your components will be easy to navigate. It will be easy to oversee the architecture of your system in the components, and that facilitates for developers finding their way through the code base. And it will be also easy to do isolated maintenance on isolated parts of your code base. To show you how these guidelines work in practice, we start first with the guideline for modules. The guideline for modules tells you to limit the size of modules to 400 lines of code. Again, we extracted from the Jenkins open source code base the largest modules that are in that code base. And remember, for Java, when we say module, we mean the class level. On this slide, you see the modules in Jenkins that are over 400 lines of code. Jenkins contains many classes, and many of them are below the 400 lines of code threshold, but these are the biggest classes in Jenkins, and they are over the 400 line threshold. Again, these are classes that are over or fairly beyond the tipping point of our guideline. The problem with large modules are that large modules tend to become maintenance hotspots for new code. When a module is large, and this is comparable to a large unit, over time in maintenance it will grow only bigger and more complex. So the same effect that we see on the unit level also occurs on the module level. Sometimes we also call this the snowball effect. Large modules are especially a problem for new developers or less experienced developers, because due to their size they become very hard to understand and very hard to maintain. Sometimes they even grow to a size that they become what we call no-go areas for new or less experienced developers. As an example, if we look in the Jenkins code base, the Jenkins continuous integration server, the core of the functionality of Jenkins is the scheduling logic, and all of this logic is contained in a single module, which is the queue class. And although there is structure inside this queue class, we see a lot of inner classes, still the total lines of code in the queue class is over 1500. And of course there are also inside the classes a large number of methods. And This is a part that is a core functionality of Jenkins, and probably there is not a lot of maintenance on that part of the code base, but this is a very complex and intimidating part of the code base, and it's hard to maintain for new developers. If you limit your modules to 400 lines of code, and you also limit the size of your units to 15 lines of code, there will be room for about 25 units inside your modules. Using these guidelines, you keep the concerns within your code base separated, and you prevent very large modules that are very hard to maintain from growing inside of your code base. Now to the two guidelines that we have for the component level. Again, this is the dependency graph that Željko showed in the beginning of this presentation. And we actually have two guidelines that help you in preventing your code base from becoming this quite impressive but unmaintainable dependency graph. The first guideline is about the number of components, and it tells you to limit the number of components to around 6 to 12. The second guideline is about the dependencies between components, and that guideline tells you to prevent any cyclic dependencies between components in order to keep a clear relationship and also to allow developers to do isolated maintenance. The title of this slide is that developers on your team should be able to draw the high-level architecture of a system in no more than 5 minutes. If you have a limited set of components and a clear dependency relationship between components, all the developers in your team will be able to draw the architecture of the system on a whiteboard. And this will also prevent your code base from becoming what is here on the slide, a fairly tightly connected, hard to understand code base. So we have two guidelines for the component level, one about the number of components, the other one about the dependencies. And to make it clear what we mean with the guidelines, we have an example of a componentization of your code base that is compliant to the guidelines. On the left, you see a architecture, a component picture of 8 components that have clear, directed, non-cyclic dependencies. The components are named C1 to C8, but imagine that this is a web application, and the top components are your presentation components. Perhaps there is a web and a mobile part of your system. The lower components, say C4, C3, and C5, contain the business logic of your system, and say components C6 and C7 contain the persistence logic. This is a layered architecture, and if you make sure that your code base is separated on the component level this way, it becomes easy for developers to navigate through the code, and it also becomes easy for developers to do isolated maintenance. A risk when applying these guidelines is what you see on the right of this slide. And the first two diagrams on the right, they show you where the number of components is not in line with the guideline. The first picture shows you a system where there are only 3 components, and clearly the size of these components is not balanced. So, for example, it becomes difficult for developers to find their way through the system to locate code when to do maintenance. And the other picture is a component diagram that is the opposite, that actually has too many components. This is also difficult for developers, and especially for less experienced and new developers, to find their way through the system. A benefit of having a limited amount of modules and having clear dependency relations defined between your modules is that you can spot cyclic dependencies early on and prevent them from occurring in the system. For example, at the right-hand bottom of the slide, you see a violation introduced, a cyclic dependency between module C7 and C2. And this is actually much easier to do if you have clearly defined relationships between your components. So you can prevent it from happening and hopefully prevent your system from becoming a dependency graph that we've seen in the beginning of this presentation. The last guideline that we would like to present to you today is for the system level. This guideline is pretty simple, but achieving it can be a very challenging task. The guideline tells you to keep your codebase volume below 200,000 lines of code. We set the threshold value for this guideline based on the team size that is required for building a system. And on an average, a developer writes around 10,000 lines of code per year. It differs a bit between different programming languages, but this is an average number. And from our practice, we see that this turns out to be a pretty accurate number. If you limit the system to the system size to 200,000 lines of code, that implies that also the development team is limited in size. To produce 200,000 lines of code, you can do that with a fairly small, say around 7 to 9 people of development, and it will also take you a fairly reasonable amount of time. Another benefit of having a system and a limit on the total size of code is that after the system is being produced and it goes into maintenance mode, you need also a smaller team to do maintenance on the code base. And a third limit is that the limit on lines of code also puts an implicit limit on the functionality that is implemented in a system and also on the stakeholders that the system has. These are what we experienced as success factors, or actually we've seen a lot of systems that are over this 200,000 lines of code limit and that are suffering from large development teams, a large amount of stakeholders, and actually are hard to maintain. So, to summarize the guidelines that we've presented to you today, let's go over them quickly one more time. 4 of the guidelines apply to the unit level. Those are the first 4 guidelines. And remember, a unit is a method or a function or a procedure, depending on your programming language. And we have clearly defined thresholds for the size, complexity, number of parameters, and duplicated code inside units. The 5th guideline deals with modules, and that guideline tells us to limit the size of modules to 400 lines of code in order to keep a clean separation of concerns in our system. And the 6th and 7th guidelines deal with the components. Those are the high-level architecture components of your system. And we advise you to aim for a set of 6 to 12 high-level architecture components with clear dependencies and to avoid cyclic dependencies at all times. The last guideline is about the size of the system, and to keep your system maintainable, we advise you to keep the size of your total code base below 200 lines of code. For the takeaway message that we have, We've talked about sustainable software and how we find that we talked about sustainable business and how maintainable software can support a sustainable business. We also talked about what we consider maintainable software. And we think that maintainable software is software that is being written with maintainability in mind. And we presented a set of simple guidelines that can be followed by all developers all the time. And it's important that they do so in order to create maintainable code. Maintainability is something that we think should be addressed from the beginning of a project. And maintainability does not mean a perfect code base, but it should be something that is on the mind of every member of the team, and every development they do should be compliant to a small set of maintainability guidelines. The guidelines we presented today, they are simple. They contain clear thresholds, the tipping points, but we experienced that applying the guidelines in your daily software practice can actually be quite challenging. It takes actually a lot of discipline and experience if you want to write consistently maintainable code. We also found out that this is a skill that can be learned. It doesn't take 5 to 10 years of industry experience before you can build maintainable software. But you need to practice, and for that we think that training on this topic helps. Currently we are preparing a book and a training on how to build maintainable software. And for example, in that training you will learn how to apply the guidelines that we presented to you today. If you want to know more on this topic or bring this message to your team, please visit the link at the bottom of the slide where you can find more about our upcoming training and certification program. So that completes most of the slides that we prepared for today. I guess we have time for a couple of questions. Okay, there are quite a couple of questions, and we selected a few of them. First question we have here is a question from Humberto Sanchez, and it's about the unit test code, if that is included in the total code base size. Actually, it's a very good question, because today we haven't talked about the difference between the what we call production and testing code. But in short, the answer to your question is when we mention the 200,000 lines of code, we actually mean production code. Of course, we find it very valuable if the developers write unit test code alongside their production code. Actually, writing test code is very crucial to building maintainable software. So this number does not include the unit test code, but yeah, for sure we think unit testing is very important for maintainability.
Yeah, and you should have as much as possible unit test codes.
We have another question on the total size of the code base. This question is from Mr. Abbott, and the question is, do you exclude code that is maintained by a separate team, such as frameworks, libraries, or major subsystems? Yeah, actually, when we talk about the code base, the scope of the code base is the code that is maintained by a single team of developers. So this excludes all code that is maintained outside the team of developers. Maybe there is third-party code, or maybe there is internal projects that are being reused inside a system. So, in short, the answer to your question is no, we don't include all the frameworks and external code. When we talk about the code size, the code base size, we only mean the code that is being maintained by the team of developers. Another question from Mr. Lee. It's about how we are defining a line of code. Yeah, that's a good question, and we can actually go back to a slide where we show you the compliant methods. I have it on the screen now. On this slide, you see two methods, and the first one has 13 lines of code. The second one is 15 lines. And actually, our definition for a line of code is all the lines in your program files that are not comments or whitespace. So, for these two methods, all the lines that are not completely whitespace, we count them as a single line of code.
So a few more questions. We also have a question from David Ambrosa. So the question is, how did we arrive at these limits? So as we already talked briefly in the beginning, so these numbers are not our invention or intuition. They are results of statistical analysis of our benchmark. And in this benchmark, we collect data that we analyze in projects. And basically, in many of these projects, as I said, we see this tipping point pattern that you have quite a lot of elements that stay quite a long while under some values, and then when they reach a particular point, then things quickly go in other direction and reach quite a high level of complexity. So this is just one illustration of some of the statistics that we use, but these numbers are based on statistical analysis of our software benchmark.
Another question, this is from Mr. Van Kamp, and it's about how we measure units in languages like JavaScript, which have support for nested functions. Actually, it's a good question, and what we see as the units in languages are the smallest blocks of independently executable pieces of code. So that's a bit theoretical definition, but it means that if you can independently test and execute a group of code statements, then that is what we consider a unit. So to answer your question, JavaScript indeed supports the notion of nested functions. And if you follow a convention or use a framework in JavaScript that allows you to call the nested functions independently from each other, test them independently, and reuse them independently, then that's what we consider a unit.
Okay, another question, this time from Kevin Lee, about do you have tools that help track these metrics? Of course, yeah, the number of tools, we have their own tools that we are using to calculate our benchmark. There are also some open source tools, so you can visit our website to get more information. But maybe one note also to say here is that if you follow our guidelines and if you try to keep your code small, simple, and flexible, then you may not need the tools, because if the code is small if it's simple, you may basically, from looking at the screen, see this part. That's also the point of these guidelines. If you have discipline, you don't need tools. And the other way around, if you don't have discipline, tools can help, but they cannot really solve all of your problems.
Right. That's also one of the principles of our guidelines, is that we have simple, clearly defined guidelines that almost require no tools to be applied. We think this makes the guidelines more powerful during development.
But yes, we do have tools, and also, as I said, there are open source tools available.
Yeah, so another question about the code base size, which is interesting, is from Mr. Kariyavasam, and it's about how can the total lines of code in a code base be limited to just 200,000 lines of code. Of course, there are industry projects that actually require much more functionality than you can accomplish with 200 lines of code. And this is true, and actually that is a nice challenge to see how you can realize larger functionality by still limiting the size of individual code bases to 200,000 lines. So our guideline says that a single development team should not work on a code base that is larger than 200,000 lines. Of course, you can create by having multiple systems, by combining multiple systems together, you can create functionality that exceeds what you can implement in 200,000 lines per system. But then you start to go into the landscape architecture, or where you combine functionality of multiple systems.
Also, maybe add a note, because here was a comparison made with the Windows code base. So first, yeah, one approach said Windows is probably better looked as a complex system or system of systems with number of subsystems. And second is also that most of the companies that we look do not have resources and size of Microsoft. In that case, normally you're talking of small and medium-sized companies, and these guidelines are particularly aimed at such companies. So how to keep teams small, how to enable systems that can maintain system that works for most companies rather than for the biggest ones.
Okay, and folks, that brings us to approximately the top of the hour. So we are going to say a very big thank you to Rob and Jelko for being with us today and for presenting an incredible webcast for us all. And a thank you for them sharing their knowledge and expertise with us. Thank you, gentlemen.
You're welcome.
Thank you.
Also, folks, as we close out, we want to say a big thank you to SIG for sponsoring today's event and let you all know we at SIG believe that software can be improved, thus enabling people and organizations rather than being a burden. This is what we work on every day. Based on its industry benchmark for software quality, SIG advises clients and suppliers about managing software risks from bit to boardroom. This is what we call getting software right. Thank you again, SIG. Also, folks, we want to say a big thank you to all of you for attending our webcast today and hope you've benefited from it. And a big thank you to those of you that got up early or stayed up late to attend the event, as we had people joining today from all over the world. So we do thank you so much. We also want to let you know that we did record the webcast today, and we will have the recording ready within 48 hours. You'll receive an email notification with access details as soon as it's ready. Thank you again, gentlemen. Thank you, SIG. This will conclude our webcast today. Goodbye, everyone.